Welcome to the Explainer. Today we're doing a deep dive into an agentic AI architecture that is, frankly, a game changer for anyone putting these things into production. It's called MemRL, and if you've ever deployed an agent and then pulled your hair out because it keeps making the same mistakes, well, you're going to want to see this.
So let's get right to it. Here's the big, ugly problem every single one of us deploying LLMs runs into. It's called the stability-plasticity dilemma. Right? You've got this incredibly powerful, stable model, but the second you want to teach it something new to make it a little more flexible or plastic, you risk catastrophic failure. It's kind of like having to recompile and redeploy your entire microservices stack just to change an environment variable. It's slow, it's expensive, and honestly, it's terrifying.
All right, so here's how we're going to break this down, just like a proper tech spec. We'll start with a problem, then introduce the MemRL solution, this idea of a brain versus a notebook. We'll dig into the actual architecture, look at how it learns on the fly, and finally, talk about the engineering impact. You know, the benchmarks that make you go, whoa.
Okay, so first up, let's really pop the hood on this. Why are our models so fundamentally static? Why is it so hard for them to just learn on the job?
This really nails it. All the knowledge in an LLM is literally baked into its parametric weights. So if you want to update that knowledge, you have to do a full fine-tuning run. We're talking massive GPU clusters, tons of data, and a whole lot of time. And even worse is this thing called catastrophic forgetting. It's a real phenomenon where you teach the model a new trick, and in the process, it completely forgets how to do something else that was critical. It's a nightmare.
So how do we get around this? Well, this is where MemRL comes in. It's an entirely different architectural pattern, a whole new way of thinking about how AI learns. The core idea is just so elegant. Instead of trying to constantly rewrite the brain, you just give it a notebook. The LLM, the brain, is frozen. It's immutable. It does what it does best, reasoning. But all the new learning, all the experience, gets written down in this external, dynamic notebook. From an engineering perspective, this is just beautiful decoupling.
And this slide just lays it all out. On the left, you've got the old way, parametric learning, where knowledge is physically part of the model, super expensive to change. On the right, you have MemRL's non-parametric world. Here, knowledge is just data stored externally. So learning isn't a massive retraining job anymore. No, learning is as simple and as cheap as updating a row in a database. It's a total paradigm shift.
Okay, let's get into the nitty-gritty. What does this notebook actually look like at the data structure level? How does it all work under the hood?
So every memory, every experience is stored in this simple but powerful three-part structure. It's a triplet. You have the intent, what the agent was trying to do, you have the experience, what it actually did, and, this is the key part, you have utility, how well that action worked out. It's not just a memory of facts, it's a memory of cause and effect. And here's what one of those triplets might actually look like. It's basically just a JSON object. The intent is a string, refactor user off module. The experience could be anything, a pointer to a script, a specific code trajectory, maybe even a git commit hash. And then there's the utility, the Q value. Think of it as a confidence score. This particular strategy for refactoring has a 92% success rate based on past runs. That is incredibly useful information.
So when a new task comes along, the retrieval process is a really clever two-step dance. First, it does a standard semantic search to find all the past experiences that seem relevant. But then, and this is the magic, it re-ranks that list based on the utility score. It doesn't just pick the memory that sounds the most similar, it picks the one that has actually worked the best in the past. It's the difference between blindly copy-pasting from Stack Overflow and using a solution you know has passed code review.
Now this is where it all comes together. How does this system actually get smarter? How does it update those utility scores without ever touching the core model? It's a classic reinforcement learning loop, but it's applied so elegantly here. The agent tries something from its memory. Then the environment gives it feedback. In a software context, that environment could be your CI/CD pipeline. Did the tests pass? Success. Reward is high. Did the build fail? Failure. Reward is low. That feedback loop directly updates the utility score of the experience the agent just used.
And this is the math behind it. If you've ever touched reinforcement learning, you'll recognize this instantly. It's a basic Bellman update. You're just taking the old Q value and nudging it a little bit based on the new reward R. The key thing here for us engineers is how incredibly lightweight this is. This isn't a GPU melting operation. This is a simple floating point calculation you can run on a CPU in microseconds.
So the architecture is cool, The theory is sound, but what's the bottom line? What does this actually get us in terms of performance? Let's look at the numbers.
A 56% performance gain. Let that sink in. In benchmarks like AlfWorld, which are all about complex tasks that need exploration and trial and error, MemRL blows a standard RAG agent out of the water. This isn't some tiny, incremental improvement. This is a massive leap forward in capability.
And this chart just makes it painfully obvious. Your standard RAG agent succeeds about 40% of the time. Not bad, but the MemRL agent, because it's actively learning from every success and failure, pushes that success rate over 62%. It's literally the difference between a new intern who just asks a lot of questions and a junior engineer who learns from their pull request comments and actually gets better over time.
And you can immediately see how this applies to the real world. Think about a coding assistant that actually learns your team's specific coding style and which refactoring patterns always pass your unique test suite. Or a logistics robot that learns the actual messy reality of the warehouse floor instead of just relying on a perfect blueprint. The possibilities are huge.
So, to sum it all up, this table says it all. Traditional RAG is a passive system for accessing knowledge. MemRL is an active system for evolving skills. And the kicker, from an infrastructure and cost perspective, is that last row. The update cost is minimal. We are talking about tiny, real-time CPU-based updates versus costly, slow, GPU-based fine-tuning. For any engineering leader, that's a massive win.
And that leaves us with a really fascinating question to think about. For years, the whole industry has been in a race to build bigger and bigger brains, these enormous static LLMs. But maybe, just maybe, we've been focusing on the wrong part of the equation. Maybe the real key to building truly smart, adaptive, agentic AI isn't a bigger brain, but a better notebook.